Hello, my name is Luis Garabito, and we're in ESA 2.0. As a team lead, I had the idea to create a long-range navigation system, which was the communication between the rover and the drone. The drone was tasked to basically search the area for any objects in its area and communicate to the rover. Now, several hills we had to overcome were time constraint, coding knowledge, and also faulty materials. The team members are Crystal Borja, Salvador Martinez, and me, and I, Luis Garabito. Now, initially, our project, we were to create an Arduino board. We were to use an Arduino and hook it with the Bluetooth module on the drone to communicate with the rover down below. Unfortunately, when we got the materials, we saw that they were too big to actually put on the drone. So we had to approach this project in a new direction. But as we thought of a new solution, object tracking, that was also not working out. So we had to simplify the project even more. Instead of making it autonomous like we wanted to, we had to basically make it pre-programmed. So we would have to have the drone fly up, scan the area, come down, and then have the rover move forward, stop, turn right, and let the drone once again survey the area until it's finished. Now, problems or several obstacles I had to overcome while creating the rover were that the first version of the rover was not working well. The motors weren't working well. The wires themselves were pretty bad, I believe. And then the second problem was that my Arduino SparkFun board got fried, so it wasn't allowing me to proceed with the project. So what I had to do in order to circumvent this problem, I had to actually buy an Lego Uno kit, which allowed me to build and program a rover, allowing me to continue with this project. Now, several things that I actually learned in this project were how to use multiple driver shields. I learned about what an H-bridge and how it functions. And I also learned more about the Arduino in general and different types of Arduinos and drones, of course. The experience of this project, what I've experienced was frustration, fulfillment, and overall satisfaction with what we have. I feel very honored and also very, very happy with what we have. And not only that, I'm also very satisfied and very exhilarated to have met all these people and created these new bonds.
Hi everyone, my name is Crystal Borja and I was responsible for programming the drone. I'm very new to Python programming, so in the beginning it was a bit of a challenge. However, I was able to use PyCharm IDE to control the movements of the drone, how high it flies, and also object track. When working on the drone, I did encounter a couple of issues. For example, the battery life was really short and the drone seemed to overheat quickly. To resolve these issues, we assumed in the beginning that the overheating was caused by the battery. So a teammate of mine did order an extra battery to see if that would help the issue. However, it didn't and the overheating persisted. So to fix that and the battery life, we tried to use a simpler code to let the drone, or to make the drone not use as much energy. We also noticed that weight on the drone did drain the battery life. So to fix that issue, we did remove the propeller shields from the drone. We did use a simpler code to save energy from the drone as well. In the beginning, we did have the drone working autonomously. However, we've been having errors with our code, and today we weren't able to get the drone to work on its own. So instead, my teammate Saul will be controlling the drone through his phone using the Tello app. Thank you.
Hello, my name is Salvador Martinez, and I helped out with the drone on this project. Our first approach to the project was to mount an Arduino and an ultrasonic sensor to the drone. We found out that we can actually use the OTG cable to power the Arduino and the sensor using the Tello battery. But unfortunately, we realized the propellers were too noisy to be able to use the sensor on the Tello. So we scrapped that plan. And we decided to use a Tello camera instead. The way we approached it is we used TensorFlow with Python to be able to detect objects and send that information back to the rover. We wanted it to be able to detect objects and maybe even possibly cliffs, so the rover would know the best way to maneuver around. Another big issue we faced was the Wi-Fi connectivity. We tried to use a Wi-Fi module with the tello to get a communication, but unfortunately we could not get the communication. Even though we were unsuccessful with how we wanted the project, we still learned a good amount of coding, especially with the tello. We were able to make it fly, land in different locations where we wanted it to. And for future projects, we would actually like to make the TensorFlow work on the tello and also be able to land the drone on top of the rover, so it would be more of a one unit thing.
Hello everyone, my name is Krista. My peers Alea, Edgar, and Richard have all collaborated to design a garden rover for extraterrestrial agriculture. This project took place over the course of the summer, starting in July, and I wanted to say thank you to those that provided this opportunity to us. So let's get going. The process that went into this project consisted of 3 main steps: research, design, and assembly. In the beginning, we all began by doing research for a couple of days and figuring out what we needed to do to help plants grow on supposedly extraterrestrial terrain. Once this was figured out, we went on to actually put together a rough timeline, and we assigned roles to each other. The next step in the process was to actually sketch a design and then move on to the assembly. So going back into the research phase, we first asked ourselves, in a perfect world, what would we have to do to fix Mars soil so that plants can grow in it? And we find that there is a long list of factors that could be incorporated into this project, such as any of these macro or micronutrients, or pH level, or moisture level, or sunlight, or etc. So we narrowed it down to fit our timeline and thought that focusing on the most important nutrients would be a good idea. Well, what are they? The most commonly important ones are nitrogen, phosphorus, and potassium, which often goes by NPK. Nitrogen is known to improve a plant's overall growth, and it is also what helps the plant produce chlorophyll, which is what makes the plant a beautiful green. Phosphorus is important for root and plant cell establishment and growth, energy conversion, and it plays a key role in the plant's photosynthesis process. And lastly, potassium helps maintain the overall health of the plant. Different plants thrive better with different ratios of NPK, and it's actually what is printed on most of the fertilizer's bags. So this is what we've researched mainly in the beginning, NPK's role and how to amend the soil. We then began to do some research for the assembly phase, and we headed on into the design phase.
When designing the rover, we wanted to make sure that prototypes could be manufactured quickly, and for this reason we chose wood and cardboard for the initial prototyping and proof of concept designs. And later on, when we needed more specialized parts, we used 3D printing due to its high precision and ease of use. Some parts, such as the drill holder, required very tight tolerances, and for this we turned to 3D printing for its high accuracy in producing parts with very good tolerances. During the design process of these parts, we also required the use of precision measuring instruments that would be able to accurately and precisely give us the correct dimensions for the parts that we needed. To get the best idea about the quality of soil in a potential growing location, our rover is able to drill 300 millimeters down with a diameter of 25 millimeters, bringing soil from the bottom to the very top for sampling on our NPK sensor. The rover is capable of dealing with various conditions ranging from loose sand to extremely coarse rock that includes sand. One of the major challenges we had was actually getting the screw thread for the drill platform to actually move up and down, because we weren't able to get the NEMA 17 stepper motors working in time to actually incorporate it into the final design. So we resorted to using a cordless power drill for supplying the amount of torque that we needed to move the platform up and down.
What I did for this project was use my basic C++ coding skills to create a program that has 4 functions. You can access the program through the Replit link on the bottom of this slide. The first function of this program is basically a ratio calculator. The program asks the users to input the measurements of NPK given from the sensor, and it'll give a ratio of those values. The NPK sensor gives back measurements which are in milligrams per kilograms, which is milligrams of substance per kilograms of weight. NPK ratios are more commonly used than the actual measurements of each substance. NPK ratios are typically found on fertilizer bags. The second function of this program is to save a ratio. The program asks the user to enter a name for the ratio and the ratio numbers, and it'll save it into a text file which can be accessed in the third function, which will basically just print the saved ratios onto the user screen. The fourth function gives an NPK amendment suggestion. The program asks the users for the NPK amounts like in the calculate ratio function, then asks the user to enter the desired ratio. The system will then display how much to add of each substance and the total amount that would be in the sample. So this is the program that I had wrote up for this project, and on the next slide I wanted to show what an NPK sensor looks like and our experience with it. So what you do with the NPK sensor is you put the 3 prongs into a dirt sample and it'll give you the amount of NPK in that dirt sample. I tried to hook it up to the Arduino breadboard and had a hard time connecting the wires into the allotted spots as the wires were very short, as you can see, and I was very nervous on cutting off the covering around the wires to make them longer, so we were unable to do that, and we were missing the 485 to USB converter, and so we were unable to get it up and running with Arduino or computer. However, we were able to get its measurements for a part of the rover design that Richard had made. And with that, I hand the presentation over to Richard.
Originally, we intended to make the soil testing rover, but due to distance learning and limited time, we wanted to show a proof of concept in the form of a mobile lab station for the NPK sensor. So here we have our initial first sketch in the bottom left corner with a little arm that swings up and down that allows us to test and spin the soil with the screen and storage for other parts of the lab. After coming up with the initial design, I took the design into SolidWorks and designed this assembly shown on screen. In the top left corner, you can see the assembled design made up of 8 parts, and in the bottom left corner, you can see the exploded view of the 8 parts of the assembly. It features magnets that hold it together and a 3D printed design in mind to minimize waste. After designed in SolidWorks, we went ahead and planned to 3D print all of the 8 parts. It was 3D printed on a Cheetah X Plus 3D printer, as well as sliced on the Cheetah slicer. The whole entire assembly took 35 hours to print at 20% infill at 50 millimeters per second. And due to the design, there was very little cleanup, and the whole entire assembly snapped together. Here you can see the fully assembled prototype of the portable lab station. It features vials, paperwork, and tool storage, as well as a pivoting arm and serviceable compartments for the Arduino and electronics. While not fully functional, it illustrates some of the core ideas and concepts that we could have used if we had enough time to complete the rover portion of the project.
So hi, my name is Martin Duran, and I'm the rover designer for NASA Express. And this is Jaswant, and he is the coding/feature designer for NASA Express. And the basic idea behind our project is we wanted to have a rover that you can easily send it from point A to point B. And the reason we thought this was a good idea is, like, for example, the upcoming moon Artemis mission is going to be prohibitively expensive to even send people to the moon. So we wouldn't want those people to be spending their resources doing menial tasks like going from point A to point B, when this is something that can already easily be automated. And along with the cost issues, there is also like safety issues for our astronauts that we're trying to get around by using this project. Like, for example, we don't want our astronauts to be exposed to the harsh elements of outer space, and especially when we can just send a rover to transport these materials. And this is a menial task that's already like easily automated. And this is the kind of basic inspiration for our project.
This is a product of our rover. When I press this button, the rover will move forward until the IR sensors detect an object in front of it, and then it will stop. So.
Materials that we chose for the project, we went with the SparkFun red board, and the reason we chose this board is because it's an Arduino-based microcontroller, which makes it really easy for us to connect any modules that we wanted to. Like, for example, we used the NRF24L01 wireless communication module in order to be able to send radio frequencies from the transmitter to the receiver Arduino, and we also have the motor driver just to control the DC motors. And as well as that, we have like this infrared sensor. It's just so the robot can kind of see where it's going.
Going over the possible upgrades for the rover. So the first upgrade to do on the rover is to get something that's a bit more long range, as the infrared sensors that we are using are a bit short range, and the only reason that we're using them on the rover for now for the demo is because they are a long enough range for object detection and to avoid crashes. The second upgrade to possibly do is to not use the ultrasonic sensors that we have, although we are using them for this demo. But there is no atmosphere on the moon for the actual sound waves to travel.
I really enjoyed working on this project for a couple of reasons. The first reason is I did just learn in class about electricity and magnetism in my physics classes, and it was really nice to get some hands-on experience working with the actual circuits and like getting things running. And especially now during the COVID pandemic, since it was really hard we didn't have labs and we couldn't even see anything physically. And the second reason I really like working on this project is because I could really put my programming skills to the test. I've already taken classes before with C++, and it was nice to be able to work at the programming language that was familiar and then get something that actually interfaces with the real world.
Hello, my name is Dustin Moore. My partner's name is Jonathan Nahazol, and our project is a lunar survey rover.
So our rover has been inspired by some of the different rovers that have been used over the past decade in order to explore outer space. And our particular rover specializes in data collection. So what our rover can do is collect and return data about temperature, humidity, as well as the rover's spatial orientation and position. And to do this, we have mounted several different sensors and are able to control the rover using a Bluetooth module connected to a four-wheel chassis. We've also outlined certain goals that we hope to have achieved by the time of our completion of the project. Specifically, we wanted to build a vehicle that utilizes various sensors capable of analyzing their environment. We also wanted to gain a greater understanding of the world of programming and circuits. And finally, we wanted to gain practical engineering experience.
This is a list of the materials we used in our project. Here's more of the materials we used. This is the chassis that we used in our design. We designed our rover to have the following features: temperature and humidity readings, object detection and velocity readings to place it spatially, and then we wanted this data to be displayed on the serial monitor on board the rover with an LCD monitor, as well as through the app that would also be used to control the rover.
The first sensor we have is a Grove 6-axis accelerometer and gyroscope. So what the accelerometer does is it can measure acceleration in each axial direction in G's. And then these values are then taken and used to determine the roll and the pitch of the sensor. And the roll and the pitch are referring to the orientation about the X and Y axes. The gyroscope is able to measure angular velocity and DPS, which is degrees per second. And these values are then taken and converted to RPM, which is revolutions per minute. Next, we have the HCSR04 ultrasonic sensor, and what this does is it sends out a pulse that reflects off of an object back to the sensor, and the time it takes to return is used to determine the distance of the object given the speed of sound. Finally, we have the DHT11 temperature and humidity module, and this can determine the average ambient temperature and humidity. The temperature accuracy is plus or minus 2 degrees Celsius, and the humidity accuracy is plus or minus 5%.
This is a diagram of the wiring for the motors in our rover. Our design uses a motor driver to supply the motors with the higher voltage they need, and a Bluetooth module to wirelessly send and receive data. This is used to communicate the sensors to the breadboard, as well as send the commands to control the movement of the rover. To control our rover, we decided to design our own app. It connects to the breadboard via Bluetooth, and it sends movement instructions, as well as receiving and displaying the data from the sensors on the design. And it was made using MIT App Inventor. To control the movement of the rover, the app sends a single-digit code that corresponds to a specific command. The app organizes the data received from the sensors by dividing it at pre-designated points and displaying it appropriately in real time. This is the finished rover once we attach all the sensors and the LCD display. And this is a demonstration of our finished vehicle and app.
This concludes our presentation, and we'd like to thank everyone involved for the opportunity as well as their investment in this project.